Thanks for the introduction. A famous proverb says, a small leak will sink a great ship. This is easy to transfer into to the pipeline industry, where often these small things create the biggest trouble. When there are undetected pinholes that grow over time and lead to certain leaks, for example. In this presentation, I will introduce you a technology, an inline inspection technology which was developed to detect and size even small pinholes and provides a resolution which is comparable to laser scan technology. So a big improvement of MFL-based technology in the end. And with this, I welcome you, every one of you, to the presentation MFL-A Ultra, making the invisible visible. What I would like to talk about is just point out some pipeline operator challenges, then give you an overview over the changes that we made, that ROSEN made to improve the resolution. I will then show you a case study where we were able to detect certain pinhole features. Then, of course, show you something about the benefit that a pipeline operator can have and will have when using the Ultra service. And I will end this with a short conclusion. After my presentation, there will be time to ask questions, and of course, I try to answer them all. Pipeline operator challenges is always to increase the asset performance, to operate safe, to somehow be responsible for the asset lifetime, that you have a long asset lifetime. But certain, the inline inspection technologies that are currently available often don't have a high enough resolution to evaluate certain defects. This can lead to a very conservative integrity calculation, which in the end might lead to unnecessary digs. And digs are indeed, some of the most expensive things that you can have. So resolution was until now not high enough. The data evaluation, as it was until now, is dependent on the human factor. So it's always possible that there are some human errors, and this impacts the repeatability of results. And as mentioned, integrity assessments are quite conservative, and if the resolution is higher, then you can get a more realistic result. As mentioned, certain defect types are not easy or very hard to detect, and sometimes with current standard technologies not able to detect. Some features are shown. We are talking about highly corroded pipelines, MIC pinholes, complex corrosion, top-of-line corrosion, and even girth weld defects. This is very challenging to see defects in girth welds. With the Ultra technology, this will be possible. To somehow compare the development that we made is somehow we can go to the medical imaging, where the common technology, which was very successful, the X-ray technology, but there's always some space for improvement, which led to the 3D CT, and this was a step change in technology. So the question is, why not doing the same for inline inspection? We see here a C-scan of MFL-A Ultra data with some corrosion features that you can see here. And why not creating a three-dimensional pipeline image of this part, where you can identify the defects near welds, even in a three-dimensional part. So this is now possible with the Ultra technology. But of course, some certain changes had to be made. New sensors were developed which are fully triaxial elements with three-dimensional integrated circuit modules. We have a resolution of 1.6 millimeters in circumferential direction and an axial sampling rate from 1 millimeter. Here in the picture we can see the new sensor carrier with the new sensor elements. This compared to the high-resolution standard MFL. So we were able to compromise the size of the elements and therefore increase the resolution. This gives us approximately 10 times more sensor elements per tool compared to these high-resolution MFL systems. If we compare the different resolutions, we see the MFL-A Ultra has around 4 to 6 millimeters in circumferential direction, ultrasonic around 4 millimeter, ultra 1.6 millimeter, and 3D laser scan around 1 to 2 millimeter. So we are really close to the resolution of laser scan technologies, which is a major step for MFL-A. To demonstrate this in a line plot, we see an example of a two-dimensional line plot from a complex corrosion feature. We see here is a defect. We see here some lines, some amplitudes. This is the picture that the standard MFL-A data gives us. If we then compare this to ultra data that we get, then we see we of course have much more channels, which have more lines, and then we can see this feature in a way better shape, and especially around this feature even more smaller features which weren't seen here. So the higher resolution gives you a better shape and in the end a better comprehension and the understanding of the complex corrosion features. Since we are using now three-dimensional sensors which are measuring in all three dimensions, as an example we see a 100% defect, a hole in the end, funnel-shaped, internal diameter 25 millimeter, external diameter 10 millimeter. Now we see three pictures that the sensor are delivering when detecting the magnetic response. The first one shows the axial component, the second one the radial component, and the third one the transversal component. It is possible to evaluate this feature just by using the axial component. But now that we are able to use all three axes, we use all values from all three sensors to evaluate and combine these values to one picture. And with this, we are now able to demonstrate the feature in a three-dimensional way. So this is the same feature, but you can now see, or we are able to show this in real 3 dimensions. This is, in the end, pretty cool. Of course, the tool mechanics had to be improved too. The fundamental difference between the high-resolution MFL-A tools and the ultra MFL tools are the number of sensor rings. Standard traditional MFL-A tool has the sensor carriers placed on one sensor ring. In the picture you see the magnets around and the sensor ring in the middle. And because of mechanical constraints, there's always a gap between two sensors of about 2 millimeters. If we want to improve the resolution and want to gain a resolution of 1.6 millimeters, there had to be made a change of the mechanics. It means 2 sensor rows are now used. The carriers are mounted slightly in an offset fashion to, in the end, gain 100% pipe vault coverage that you can see in the next picture for tools from 8 to 18 inch. This was somehow solved by using 2 magnet units. So those two between 8 and 18 inch always have 2 magnet units. You can see here that the different yokes, here are the magnets, sensor ring and magnets again, that they are slightly mounted in an offset fashion. So this means you gain the 100% pipe volt coverage. For tools larger or equal than 20 inch, it is 1 magnet unit with a sensor ring that has again 2 sensor rows, again with a slightly offset fashion. And this gives us the opportunity to gain this high resolution of 1.6 millimeters. The data evaluation also had to be improved because we are now in a state that we don't only have 1 data set, but now since we are using two sensor rows or sensor rings, we receive 2 data sets which have to be normalized to gain 1 image of the pipeline. This is a picture where it shows the 2 different data sets somehow not very clear. After a normalization and alignment of the 2 data sets, we receive one pretty good image of defects or whatever it is in the pipeline. This leads to a significant quality improvement for this higher evaluation accuracy. Autodata is the next step that we are already using. It is based on machine learning. So the whole process and the whole chain of evaluation is based on machine learning, which means we have ILI data, pre-processing, active learning, quality assessment report, and central data service. And the big change is that we now use 3D laser scans of defects, of real-life defects, and we fed the machine-learned auto-data algorithm with those laser scans to further improve the evaluation after every run. So in each run, we use laser scans from the field, fed the algorithms to get these automated algorithms better and better for any run. So in the end, we achieve a more accurate, reliable, and reproducible results with less human impact or human error. A case study. As mentioned before, this case study deals with pinhole sizing. We received an 8-inch blind test spool, which was unknown to ROSEN. It has a wall thickness of 9.5 millimeters, and we were asked to detect pinholes with metal loss greater than 10%. The results of this test were very impressive, even for us. 7 out of 7 pinholes were found, detected, and sized correctly with a diameter larger than 5 millimeters. 7 out of 7 pinholes with a diameter of 5 millimeters were detected and sized correctly. 6 out of 7 pinholes with a diameter of 3 millimeters were also detected and sized the right way, even though the specification and the performance of the tool were only covering this for defects with diameters of 5 millimeters or larger. And in the end, 4 out of 7 pinholes were detected that had a diameter of 1 millimeter. They couldn't be sized, but we were able to detect them. An example of this test is this data that the Ultra tool gives us. We see features of a diameter 5 millimeter defects. We reported these depth of 17%, 20%, up to 92%. Below you see the actual depth that were provided by the client. The 4% pinhole wasn't detected by us, but it wasn't in specification because we start at 10% metal loss. After that, we reported 17%, the real depth was 15%, 20%, 25%, 51, 47. So the accuracy during this test was within a range of plus minus 8%, except for the deepest feature. There we see a discrepancy of 13%. This is more or less due to the lack of field verifications with defects greater than 80%. We use the field verifications and the 3D laser scans in the end to further improve our sizing algorithms. And at that time, we hadn't had enough data from the field to get this auto data development and auto data evaluation for those large defects very correctly. In the meantime, we received more and more results, so the sizing is already better now. The benefit for a pipeline operator is you receive a more realistic effective area, which means if we compare these boxes from the MFL-A, the high-resolution MFL-A technology, we pick out this box. This gives an effective area which looks like this. The resolution of the Ultra technology is now higher. That means those boxes can be Now we have some technical problems. I try it this way. We see this box was split into several smaller boxes with a higher resolution of Ultra, which leads to the identical length and depth of the feature, but a less effective area. This means, in the end, that the estimated repair factor that is calculated out of this is more realistic and less conservative. This means, in the end, that you will have less dig-ups because of better and more accurate estimated repair factors. As a conclusion, just to summarize this up a little bit, we are able to provide reliable and lifeline pipeline images. It's until now the highest inline inspection resolution in the market. We were able to detect pinholes down to 1 millimeter in diameter. The precise auto data algorithm, which is more automated than before, which is more accurate and where we improve this evaluation after and with every inspection. And in the end, a conclusive integrity assessment which shows more accurate depth profiles, higher sizing accuracy, and in the end, which reduces the conservatism of integrity calculations. And in the end, this will save money from pipeline operators. So the Ultra technology is it's kind of premium service, and if there are any highly corroded pipelines or any pipelines which were inspected by other technologies but failed in any way, then MFL-A Ultra could be a solution. Thank you.